Hello, my name is James Schiffer, and today I'm going to be presenting my simulation of a processor optimized for block cipher algorithms. This is basically what a block cipher algorithm looks like at its most basic level. Our processor is going to be taking in the key and the plaintext as data that it uses an encryption function as ASM code to operate on, and outputs the encrypted data as the result. In order to do this, we have some goals. We are going to be optimizing for throughput rather than latency. We need this to be clock accurate, but not hardware accurate. And we're going to test it with an idea algorithm. We're going to use this opportunity to learn and experiment as much as we can. So, we only have 14 instructions we can work with. And we have a 32-bit wide memory. We need to simulate all major components. I simulated the ALU, the registers, and the memory, as well as the pipeline. I implemented a pipeline, which was really awesome. And we also must keep track of the machine state, which is why we needed to do the registers and the memory. And we also need to store the memory map as a text file. So, in our DI encryption, basically, this is how it works. We load a 64-bit block right here, and then for 8 times we do this kind of an operation, and this includes a bunch of modulo operations, which you can see the Python code for right over here. Basically, it just implements a wraparound, and you do that with using a bunch of keys. You have 52 keys that you need to use, and a half round at the very end. Things to note about this: we only have one memory access, so by Andel's law, memory is not a big thing. Jumps, you can write that without using any jumps, so jumps is not necessary. By Andel's law, where we need to focus on our optimization is ALU, that is our R-type instructions. I say R-type, thinking that you know what that means, but whatever. We'll get to that in a second. So computing keys is the one thing that we're going to do as well in our simulation, even though we don't need to. It was an interesting problem. I just wanted to try it out. Basically, how you do this is you have to take the original key and you rotate it left by 25 to get the next set, and you keep doing that until you get all 52. However, we have no shift left instruction, and what we have to do instead is we have to use the multiply. To shift left by 25, you do a multiplication by 2 to the 25th. And you can use an overflow register to save the overflow and then put that into the next set of data. And you can do that, basically, I show how it's done right here. I won't spend too much time on this, but believe me, it can be done, and I implemented it. Now, for instructions, we have our I-type instructions, and these have a load, store, branch if 0, branch if equal, branch if positive, branch if negative. Notice that the load and the store right here take 14 and 13. They take significantly longer because I simulated them using memory and a CPU at these characteristics. Now, for instructions, we have an R-type. Thing to note about here is that multiply does take longer than everything else, which is true. And then we have our J-types, which are actually kind of really boring in here, and I also changed this around a little, but you'll see that in a second. Now, for choosing an ISA, we wanted to do something that had a lot of registers and not a lot of memory access. We needed registers to hold keys, and we didn't have a lot of memory accessing, so putting that as a part of our ISA didn't really help us in any way. Now, when we're choosing our ISA format, we know we definitely want registers right now. We know we want more than 52, so let's choose 64. And the size of our registers are going to be 32 bits because we need to do multiplication to do our key generation. And we need to do multiplication on 32-bit operands. So our addressing modes, that's a little complicated. I'll get to that in a second. The width of our instructions, this was an actual easy choice. Our bit width was 32, so I decided to go with 32. Variable was an option. It would have solved our register issue, but whatever. Now, to have our different addressing modes, basically we have iType. We can use Word. That's an easy thing. For our R-type, well, our keys are 16 bits, and if we made the upper half and the lower half individually addressable, we could get away with 21 registers and have tons of registers to play around with in our assembly code. So in order to do that, we have to implement a special type of operation for each R-type instruction. So here's the common one, which is word. You can see that right there. Here's a lower half word typed instruction. And here's an upper half type word operation. And here's a swap with a destination of the lower half word. And here's a swap with a destination of the upper half word. These came in these were very useful when I was doing the IDEA algorithm. Here is our ISA. You can see that we basically just made our register addresses bigger and reduced everything else. So for a microarchitecture, basically we're not very memory heavy, but we're very ALU heavy. If our pipeline depth is 5, we need to have redundancy on everything by 5. And what I mean by here is memory ports times 5, register ports times 5, and ALU actual like functional blocks times 5. Now, for special registers, we basically have a flag for modulo operations and flags that store that kind of tell you something about the last operation that the ALU had. And for pipelining, we have all of these stages that we need to implement, but not all instructions will use all the stages. For our pipeline hazards, if we had redundancy equal on our hardware equal to our pipeline depth, this one is taken care of. And let's talk about data hazards and control hazards. Data hazards can be taken care of using this kind of a method where if you have a destination register in an instruction, you set the dirty bit for it, and if the source registers are dirty, you stall the CPU until they're clean. That comes into use in our control hazards, where basically we make our a conditional jump reliant on a previous R-type operation. And we basically have the conditional jump stalled until that operation is completed, and then use that flag I showed you before to determine if the branch was taken or not taken. No need for branch prediction there. If we use preloading, hey, we can get away with a lot. We can actually speed up the program quite dramatically in many ways, which is pretty nice. So that was definitely a cool thing to implement. But as soon as we started to get deep into it and we started having execution cycle length more than 1 for our multiply instructions, our CPI and our percentage of stalls increased dramatically. In fact, it increased, so you can see right here, for each extra execution cycle spent on multiply, our CPI went up quite dramatically, as well as the percentage of stalls that we had. If we had implemented a multiplication execution cycle length of 7, it would have been 55% stall. So that's a big weakness. You really need to make your ALU very, very fast. And I think actually more than make your ALU fast, go super scalar. Implement pipelining and also implement multiple CPUs, multiple processors. And those are some of the weaknesses. And in conclusion, I made a crazy ISA with an equally crazy microarchitecture. It was a great learning experience. I wrote over 2,000 lines of Python. I really want to get into it more. I want to break out some of the bugs, and I just want to make it generally